Ma'am, you can start.
Yes, sir. Yes, good morning, students. So yesterday we were discussing about structure of atom. So today we'll continue that. So last class we had discussed about the atomic models, right? So we had discussed about the atomic models. So first we had discussed about the fundamental particles. So different particles, subatomic particles of electron, of an atom, right? So which are that electrons, proton, neutron, we saw its charges, then mass, okay. So different type of atomic species. We discussed some of the questions based on that. Then we saw two main models, atomic models, Thomson model and Rutherford's nuclear model of atom, right? Then we had discussed about the electromagnetic radiation. So it has a dual nature. We discussed that it has a dual nature. That is, it is acting like a wave. It has wave-like properties as well as the particle-like properties. Then we had discussed about the various characteristics of a wave. Okay. So we had discussed about electromagnetic spectrum. So how the various electromagnetic radiations are arranged, right? So then we were discussing about the particle nature of electromagnetic radiations. So Planck, he gave a formula that is E is equals to h nu, where nu can be replaced by C by lambda. So how C is equals to, what is the relationship between light, Planck's constant, and lambda is with mu is that C is equals to mu into lambda. So by substituting the value of mu, so you get this h is equals to C by lambda. Okay. So what is Planck's constant? Planck constant is 6.624 into 10 raised to minus 34 joule second. Okay. Then we had discussed about black body radiation. So the radiation emitted by black body is nothing but black body radiation. And what is photoelectric effect? So whenever you strike a beam of light on a metal surface, within no period or no time gap, there will be emission of electrons. Okay. So this is nothing but photoelectric effect. So kinetic energy is calculated as half mv square is equals to h nu by minus h mu naught, where mu naught is the threshold frequency. It is called as the minimum frequency which is required to remove the or to eject the electrons. Okay. So based on that, we had discussed some of the problems on electromagnetic radiation. So today we are going to discuss, we have to start with line spectrum of hydrogen. So what is line spectrum of hydrogen? Okay. So the wavelength and wave number of different series of lines can be calculated by using this formula. So this is the formula. Okay, so this is the formula which is given to calculate the wavelength and wave number of different series of line. Okay, so what is line spectrum of hydrogen, or how it is obtained, how the line spectrum of hydrogen is obtained? Hydrogen molecule. Okay, hydrogen molecule means what? It consists of two atoms of hydrogen. So this hydrogen molecule was taken in an electric discharge tube, and it gets dissociate. Okay, so when you take a hydrogen molecule in an electric discharge tube, what it happens? So the hydrogen molecule, it undergoes dissociation into hydrogen atoms, two hydrogen atoms. So when it gets dissociate, it absorbs some energy and it gets excited. Okay, so after it gets exciting, what if any element, okay, if you take any element and if you bombard with some energy, what it will do? It will undergo excitation. So after it undergoes excitation means what? From lower energy, it will go to a higher energy. So when it goes to higher energy, it has to come back. So when it comes back, it emits some radiation. Okay, when it emits some radiation, what happens? It will fall in, it will give some spectral lines. Okay, so that study is nothing but line spectrum of hydrogen. Okay, so how to calculate this series of line? It shows various series of lines. So this is the particular formula. So wave number, you know what is wave number? Last class we discussed wave number, lambda, right? So these are inversely proportional. So whenever you want to calculate wave number, so wave number is given as Rydberg. Okay, R is nothing but Rydberg's constant into that is 1 by n1 square minus 1 by n2 square. Okay, and if you want to find out the wavelength, so it is 1 by lambda is equals to R into 1 by n1 square minus 1 by n2 square. So when this hydrogen molecule get dissociated, okay, when it gets dissociated into hydrogen atom, so various spectral lines were absorbed. So these were the various spectral lines. So these spectral lines were studied. Okay, so which are the spectral lines? So you can see here. So just see this particular, you can see this particular diagram here, right? So this is the spectral line. Okay, these are the spectral lines shown by hydrogen molecule. So hydrogen molecule, it had shown this particular spectral lines. So you can see there are different spectral lines because when the electron gets excited, so when it comes down, you can see it will get it emits, okay, it emits radiation and it comes down to the ground state. So here you can see, so these are the different lines were observed. So these spectral lines were named by after different discoverers. Okay, so we'll study each of them. So you can see the first line. So that is the Lyman series. You can see this particular Lyman series from n is equals to 1. So you can see this n is equals to 1, n is equals to 2, 3, 4, 5, and so on till infinity. Okay, these are nothing but these are the different energy states. Okay, these are the different energy states. Okay, so now when n is equals to, so when n is equals to 1, okay, when n is equals to 1 and okay, n is equals to 1 and n2 is equals to 2, 3, 4 till infinity, it shows the spectral line called as Lyman. Okay, so it is called as Lyman because the discoverer or the scientist was Lyman. Okay, so he observed, or these lines fall in ultraviolet region, that is UV light. Okay, UV region. So when these this radiation, it falls in UV region and it is named after the scientist called Lyman. So these are called as Lyman. So your N1, what we had seen, N1, your ground state will be 1, n is equals to 1, and N2 will be from 2, 3, 4 till infinity. Okay, so these are the first series. Second spectral series is Balmer series. So these Balmer series, you can see here. So it is from n is equals to 2. Your stationary state or the ground state is 2. And N2 will be 3, 4, 5, etc. up to infinity. Okay, and these the spectral lines, it lies in the region of visible region. Okay, what is visible region? visible region. So this is the visible region. You can see, right, from 4,000 angstrom to 7,000 angstrom. This is a visible region. You can see different light here. Okay. So here, Balmer series. So this was named after the scientist called as Balmer series because the spectral lines were falling in visible region. So this is the particular spectral line, second spectral line. Then third is the Passion series. Why it is called as Passion series? Because Passion was the scientist who found out this particular spectral line. So Passion series. So what happens here? Here the stationary, it is n is equals to 3. N is equals to 3. Okay. N1 is 3 and your N2 will be 4, 5, 6, 7 and it continues up to infinity. And this particular lines or this particular spectral lines, it falls in infrared region. Okay, and these are named after the scientist Passion. So these are this is the third type of spectral lines, that is Passion series. Then fourth, you can see bracket. Okay, so these bracket series, so here n is equals to n1 is equals to 4 and n2 is equals to 5, 6, 7, right, up to infinity, and these fall in infrared region. So this also falls in infrared region and these are called as bracket series. Then the next series are P-fund series. Okay, this P-fund series, here N1 is equals to 5 and N2 is equals to 6, 7 and so on up to infinity. Okay, and these also fall in infrared region. So these are 5 spectral lines, okay, which were observed in hydrogen spectrum. So what was done to obtain the line hydrogen spectrum? Hydrogen molecule was taken in an electric discharge tube. This hydrogen molecule, you know, hydrogen molecule, when it gets dissociated, it dissociates into what? It dissociates into 2 hydrogen atoms. Okay, so whenever the atoms, when you produce energy, when you provide them energy, what it will do? It will get excited to a higher energy state, and when it goes to higher energy state, it wants to come back to its original state or its ground state. So when it wants to come down to the ground state, what it will do? It will give the radiation. Okay, it will emit some radiation and these radiations will show some spectral lines. So these are some of the spectral lines. These are the 5 spectral lines which were seen in the line hydrogen spectrum. So remember what is N1 in N1 and N2 in each particular spectral lines. Okay, so remember this. So next comes the Bohr model of an atom. So what is Bohr's model of an atom? Bohr's model of an atom. So some of the postulates of Bohr's models are, so that what, so this line hydrogen spectrum, so they had some limitation. It went to the Bohr's model of atom. So what did, according to nuclear model, so we had seen the nuclear model of atom. So in nuclear model, so that was put forth, so that was further expanded by Bohr's model. So what it had observed that, so nucleus is a positive charge and it is present in the center of an atom. Okay, and around them the electrons are revolving. So these electrons are revolving around the nucleus in certain definite orbits with a stationary states, which are having the fixed energies. Okay, so electrons are revolving around the nucleus in certain definite orbits. Okay, then second postulate was electrons revolve in this orbits which with a angular momentum in the integral multiple of h by 2 pi. Okay, so this was, so these were the main postulates of Bohr's model of an atom. Okay, then the third was radii of stationary state. So how to calculate the radii of stationary state is Rn is given by R naught into n square by z. This z is nothing but your atomic number. R naught is what? Radius of the first orbit. N is equals to number of shells. So these were some of the important postulates. Then how to calculate the energy of different stationary states? Okay, So this is N is equals to higher energy level. So here we are calculating the energy of different higher energy states. Okay. So here En is equals to minus 1312 upon N square into Z square in kilojoules per mole. So when you want to calculate joules per atom, so energy is given as En is equals to minus 2178 into 10 raised to minus 18 into Z square joule per atom. Okay, so these are the two formulas to calculate the joules. So if you want to calculate the energy in terms of kilojoules, you have to use this particular formula. And if you want to calculate the joules per atom, then you have to use this particular formula. Okay, how to calculate the number of spectral lines? So number of spectral lines can be calculated by N2 minus N1 into N2 minus N1 plus 1 divided by 2, where N2 is the higher energy level. Okay, N2 is the higher energy level and N1 is the lower energy level. So, or it can also be given, or you can calculate the spectral line in terms of N into N minus 1 divided by 2. Okay, so these are some of the problems. So based on this formulas, we are going to solve some problems. So this Bohr's model, okay, this Bohr's model had also some of the limitations. So the this Bohr's model was applicable for only uni-electronic system. What do you mean by uni-electronic system? Uni-electronic system is nothing but element having only one electron. So it was applicable only for hydrogen. It was not applicable for lithium, boron, beryllium, etc. Okay, it was applicable. This Bohr's model of atom was applicable only for the uni-electronic system. This could not explain Zeeman effect and Stark effect. Important. What is Zeeman effect? What is Zeeman effect? So Zeeman effect is nothing but splitting of spectral line in presence of magnetic field. Okay, remember this. What is Zeeman effect? It is splitting of spectral lines in the presence of magnetic field. What is Stark effect? It is splitting of spectral lines in the presence of electric field. Okay, remember, don't get confused here. What is Zeeman? Zeeman is a splitting of spectral lines in the presence of magnetic field, and Stark is in the presence of electric field. So we'll solve some of the problem based on Bohr's model of atom. Okay. So here, what is the question? In Bohr's series of lines of hydrogen spectrum, the third line from the red end corresponds to which of the following interorbit jumps of the electron for Bohr orbits in an atom of the hydrogen. So what you are going to do here? So what is given here? You have to calculate the, you have to see okay, you have to see the, just a second. So you have to see the interorbit, okay, jumps. You have to see the jumps of the interorbits. So your which series is given? It is said to be what? Your red color is given, right? So in Bohr series of line of hydrogen spectrum, you have to see what is given in the question. Okay, the third line from the red end. Red end means what? It is a visible region. Now visible region means what? Visible region means it is Balmer series. Okay, visible region means it is Balmer series. Now for Balmer series, okay, for Balmer series, so you know what is N1? What is the N1 value? You had seen this. What is N1 value? N1 value is what? N1 value is, it starts from 2, right? And what is N2? N2 will be from 3, 4 till infinity. Okay. Now here, what they have asked, what is the question asked here? You have to see the jump from, right? So your lower state is 2. From 2, it will jump to the third line. Okay, it will jump to the third line. So if you draw like this, okay, now this is, so if n is equals to 2, this is n is equals to 3, n is equals to 4, n is equals to 5, n is equals to 6. So this your n1 is 2. From 2, it will jump to what? Third line. So 1, 2, 3. So it will be from 5 to 2. So like this. So what is the correct answer? It is A, 5 to 2. So you know for Balmer series, n1 is equals to 2. From 2, see here, what is given? It third line from the red end. Okay. So you have to just see 1, 2, and 3. It is n is equals to 5. So the jump, so the interorbit jump of the electron in the Bohr orbit is from 5 to 2. Okay. Next question. The wavelength of the radiation emitted. Okay, the wavelength of the radiation emitted when in a hydrogen atom electron falls infinity to stationary state 1 would be, okay, Rydberg's constant. You have to find your what? So Rydberg constant is given. So here what you have to find? You have to find the wavelength. You have to find out the wavelength. Okay. So now what is the solution? What was the formula? 1 by lambda equals to Rydberg's constant 1.097 into 10 raised to 7, okay, per meter into 1 by n1 square minus 1 by n2 square. Now what is given here? So we have to find the wavelength. 1 by lambda is equals to 1.097 into 10 raised to 7 meter per meter. This then 1 by n1 square. What is what it is given? The hydrogen atom electron falls from infinity to stationary state. So your n1 is what? It is 1. So n1 square, 1 square is 1 minus n2 is what? It is falling from which? It is falling from infinity. So n2 is infinity. Okay. So 1.097 into 10 raised to 7 meter second. Okay. So this is your lambda. Now here what is happening? You have to find the wavelength here, right? So wavelength is equals to 1 divided by 1.097 into 10 raised to 7 per meter. So wavelength is given as what? So after calculating this, your answer comes to 9.1 into 10 raised to minus 8 meters. Okay. So we have to convert. So this, so if you take this 0, okay, out, so it will be 91 into 10 raised to minus 9. It is nothing but what? 10 raised to minus 9 is nothing but nanometer. So your correct answer is C. Okay. So like this, you are going to find the correct. So this is the correct answer. Okay. So by substituting, you see what is given in the question. Okay. Write down what are the given terms and then you have to solve. You have to hunt for the unknown quantity. Okay. So this is the way you're going to solve this question. So next. So when the electron of a hydrogen atom jumps from n is equals to 4 to n is equals to 1 state, the number of spectral lines emitted is. So we had seen this spectral lines, how to calculate the spectral lines. N is equals to n minus 1 divided by 2. Yes. What is n? So n is equals to 4. Okay. Just see. So here, so the electron is jumping from n is equals to 4. What is the correct answer? Electrons is jumping from n is equals to 4 to 1, right? So for n is equals to 4 you take and substitute and see. What it is coming? It will be correct. C, right? C, 6. So like this, so use this particular formula to calculate the spectral lines. So next comes quantum mechanical model of an atom. Okay. So quantum mechanical model. So there were two important concepts based on this quantum mechanical model. First is Heisenberg's uncertainty principle, and second is dual behavior of matter. Okay, so this Heisenberg's uncertainty principle, it tells you about what? So it is impossible to determine both, okay, exact position and exact momentum of an electron simultaneously. So this was put forth by Heisenberg. Okay, this was his uncertainty principle. He said that it is impossible to measure or to determine both the exact position and exact momentum of an electron. So this is the formula, what it is given. So this, in terms of the definition, it has been written as in terms delta x. Delta x is nothing but your uncertainty in position. Okay, delta x is uncertainty in position. So it is uncertainty in position. Then delta p is nothing but uncertainty in momentum. Okay, uncertainty in momentum. Now that is greater or equal to h by 4 pi. So this p, okay, p is nothing but momentum. Momentum is given by mass into velocity. So delta p is equals to, what is delta p? Okay, delta p is equals to mass into delta v. So substitute this value, okay, of delta p, you substitute here. What you get? Delta x, okay, delta x into m into delta v greater or equal to h by 4 pi. So this is the final equation what we get. Okay, so based on Heisenberg uncertainty principle, what he said, that we cannot determine both the position and momentum of an electron simultaneously. So this was the equation put forth by Heisenberg. Okay. So what is the dual behavior of matter? What do you mean by dual behavior? So in the year 1924, okay, in the year 1924, there was a scientist called de Broglie. Okay, de Broglie, he put forth, or he proposed that the matter, okay, matter will, like radiation, as you have seen, electromagnetic radiation, it has what? It has both properties, that is, it is having wave-like property as well as the particle-like behavior. Okay, so what de Broglie proposed, he proposed that matter like radiation should also exhibit dual behavior. Dual behavior means what? Two properties, okay, that is particle as well as wave-like properties. So like photon, okay, like in electromagnetic radiation is made up of what? Electromagnetic radiation is made up of photon. Okay, so electromagnetic radiation like photon has momentum and wavelength. So electron should also have momentum as well as wavelength. So according to his statement, the equation was given as lambda, that is wavelength, is equals to h by mv. So mv, you know how mv, right? Mv is nothing but your momentum. So this mv can be replaced by momentum. So according to de Broglie, so this is the equation what de Broglie gave. So that is lambda is equals to h by mv, okay, and h is equals to p. So this is the relation between lambda and momentum particle. Okay. So based on this, we'll solve some problems. So what is the question? Uncertainty in position of a minute particle of mass 25 grams in space is 10 raised to minus 5 meter. The uncertainty in its velocity in meter per second is. So h is what? H is Planck's constant. It is given by 6.6 into 10 raised to minus 34 joule second. So what are the given quantities? Okay, first we'll write what are the given quantities. So what are the given quantities? So mass is given. What is mass? Mass is 25 gram. Okay. Uncertainty in position is given. So uncertainty in position is what? Delta x is equals to what? It is 10 raised to minus 5 meter. Okay. Then Planck constant, you know, 6.6 into 10 raised to minus 34. What is the form? This uncertainty equation? Delta x into delta, just a second, delta x into m delta v is equal to h by 4 pi. Okay, now we know what is delta x. Delta x is 10 raised to minus 5. Then what is mass? Mass is given as 25. Okay, so this you have to convert into kg. So it is 25 into 10 raised to minus 3. Kg is what? 10 raised to minus 3. Okay, so this into delta V. So delta V, we have to find out what is H. H is 6.6 into 10 raised to minus 34 divided by 4 into what is a pi value? It is 3.14. Okay. So now take this delta V one side. Okay. This delta V one side, what will get? So this two terms will go here. So it will be 6.6 into 10 raised to minus 34 divided by 4 into 3.14 into 10 raised to minus 5 into 25 into 10 raised to minus 3. Okay. So this what? Here joules. Remember, we have to write this joules. So just joule is nothing but joule is equals to kg meter square per, okay, so per second, okay, second square. So this is the value of joule. So now what is here? What is h is joule second. So 1 second get cancelled. So here what will be the value? Here you have to write kg meter square and s per second. So here it is kg, right? Write the terms. Now here this meter, this meter and this meter get cancelled, kg get cancelled, right? So what is left? So what is the answer? Just substitute this, find out the answer. So after solving, it comes to 0.0210, okay, into 10 raised to minus 26 meter per second. Okay, so this when you write in terms of, so when you just shift this decimals, it will be 2.1 into 10 raised to minus 28, okay, meter per second. So this will be your answer, C. Okay, so this is the correct answer. So like this, you're going to solve the uncertainty problem. So next we'll see uncertainty in the position of an electron. So here you have to find the uncertainty in the position of electron whose mass is given as 9.1 into 10 raised to minus 31 kg, moving with a velocity 300 meter per second, accurate up to 0.001% will be. So your uncertainty in the position. Okay. So your velocity, uncertainty, so velocity is given. So what is given terms? So what are the given terms? We'll see. So given terms, first is velocity is given. Velocity is what? 300 meter per second. So mass of electron is given. Mass of electron is what? 9.1 into 10 raised to minus 31 kg. And accuracy is given. Okay, accuracy is given. So see here, only it is velocity is given. We want what? Uncertainty in velocity. So that we have to substitute. So accuracy is what? 0.001%. Now, so first what we'll do? First we will, so first we'll find the delta V value. Okay, delta V value 0.01% will what? 0.001 divided by 100 into 300. Okay, So what it comes to? The answer comes to 3 into 10 raised to minus 3 meter per second. So we get the uncertainty in velocity. So this is the velocity. Okay. So now next, so we have to find what? We have to find the uncertainty in position. So write the formula. What is the formula? Delta x into m into delta v is equal to h by 4 pi. So what is the unknown quantity? Unknown quantity is delta x. So delta x is equals to h by, so this will get divided by, so 4 in h into m delta v. Now substitute all. So h is what? What did I say? Joule value is what? Kg. Okay. What is the joule's value? Kg meter square. And so this is joule value. But what you have? You have joule second. So this second and this second get cancelled and you get, so write the value. So what is that? 6.6 into 10 raised to minus 34. Okay, kg meter square per second divided by 4 into what is pi value? 3.14. What is mass? Mass is given as 9.1 into 10 raised to minus 31. Okay, minus 31 into what is delta V? This is kg, right? The units. So this is kg. Then delta V is what? Delta V is 3 into 10 raised to minus 3 meter per second. So this meter second and this meter second get 1 meter second, this meter second get cancelled, second per second get cancelled, kg and kg get cancelled. So just see what is your answer. What is your answer? It will be in terms of meter. What will be the answer? It comes to 0.0192 into 10 raised to 3. Okay, so here you have to write it into terms of 1 point. So you have to convert. So just shift the decimal. You will get 1.92 into 10 raised to minus 2 meters. Okay, so the correct answer is A. So like this, you're going to solve the uncertainty when problem when you have to find the determine the position. Okay. So next we'll see what are quantum numbers. So you know there are specifically quantum numbers. So these are the so each electron will show some, or each orbital electron in an orbital is specified with some specific quantum numbers. Okay, so there are 4 quantum numbers. So principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So we'll see each separately. What is principal quantum number? So principal quantum number is determined by what? It is determined by n. Okay, it tells you about the size and energy of the orbit. So the possible values of n are 1, 2, 3, and it goes up to infinity. So when n is equals to 1, n is equals to 1 means what? The main shell. Okay, it represents the main shell. So when n is equals to 1, it is the K shell. So this is the K shell. Okay, when n is equals to 2, n is equals to 2, it represents the second main shell, that is L. So K, L, M, N, etc. So these are the possible values of n. So it tells you about the size and energy. So as well, so as the n value increases, what happens to the size? Size also increases. So the maximum number of electrons in a shell is given by how the number of electrons are calculated. It is calculated by the formula 2n square. Okay. So it is calculated by the formula 2n square. So next is azimuthal quantum number. It is denoted by what? It is denoted by L. You can see it is denoted by small l. Okay. So what it tells you about the number of subshells. So as principal quantum number, it tells you about the main shell. This tells you about the subshells, and it tells you about the shape of the orbitals. Okay. So if the value of n, for the value of n, L will be equals to 0 up to n minus 1. Okay, for example, if n is equals to 1, so n will go from 1, 2, 3, etc. And L will start from 0. Okay, so now if the value of n is equals to 1, what will be the value of L? L will be 0. Okay, so L will be 0. So if n is equals to 2, what will be the value of L? L will be 0 and 1. Okay, when n is equals to 3, what will be the value for L? L is equals to 0, 1, 2, because it is n minus 1. Okay, you have to calculate n minus 1 will be the values for L. So these are the how you are going to determine the value of L. So what it represents? If L is equals to 0, it is the S subshell. Okay, it is a S subshell. What is the shape? It is spherical. If the value of L is 1, what is the subshell? Name of the subshell is P. What is the shape? It is dumbbell shape. Okay, it is a dumbbell shape. So this is a dumbbell shape. What is spherical shape? Spherical shape. This is a spherical shape. Okay, so you have to write the, now this is with respect to X. So this is Px. Okay, this is Px orbital. Okay, so like this. So this is the shape of the orbit. Now, if L is equals to 2, if L is equals to 2, what is the shape? It is the name of the subshell is D and it is double dumbbell. How do you represent double dumbbell? Like this. Okay, double dumbbell shape. And what is, if the value of the L is 3, the name of the subshell is F and it has a complex shape. So it represents the orbital angular momentum. This L, it tells you about the orbital angular momentum, and it is given by h by 2 pi square root of L into L plus 1. So next is magnetic quantum number. So magnetic quantum number is represented by ME. Okay, so this is the magnetic quantum number. So magnetic quantum number, it tells you about what? It tells you about the number of orbitals present in the, it tells you about the number of orbitals present in the subshell. Okay, then for the value of L, for a given value of L, it will have values from L minus L to plus L, including 0. Okay, and for the given value of L, the total value of M is equal to 2L plus 1. So whenever you want to find the value of M, it will be 2L plus 1. The maximum number of electrons in a subshell is given by 2 into 2L plus 1. Now consider, I'll give an example. If n is equals to 0, if n is equals to 0, what did I say? How, sorry, just a second. So n will be having the values from what? N will be having the values from 1, right? 1, 2, 3, etc. So if you consider n is equals to 1, what will be the values for L? How do you calculate values of L? L is equals to n minus 1. So if 1 minus 1 is 0, so L will have the value of 0. What will be the M? How do you calculate M? M will calculate by 2L plus 1. So substitute the value of this L. So it will be what? It will be 1. So like this. Okay. So like this, you're going to find out the quantum numbers. So next. So next is spin quantum number. Spin quantum number is nothing but it tells you the direction of the electron in which it is rotating or it is spinning. Okay. So plus half is the spin when it is rotating in the clockwise direction, and minus half is for the electron when it is rotating in the anti-clockwise direction. Okay, so this is the 4 quantum numbers. So based on this, we'll solve one question. So which of the following sets of quantum number is correct for an electron in 4f orbital? So we have to write the quantum numbers for 4f orbital. So 4f orbital. Okay, so n is what? N is 4. Okay, n is given as 4. Now what are the possible values of L? How do you calculate L? L can be calculated by n minus 1. So what is the possible values? So n is 4. So it is 4 minus 1. So it is 3. So it will be what? 0, 1, 2, and 3. So it will have up to 3. Then M. How M can be calculated? M can be calculated by 2L plus 1. So substitute the value of L here. It will be 0. Okay. 0. Then it will be what? So M into it will be 1. So the value comes to 1. And you have to calculate for what? And one electron, any one electron. So if you consider one electron, okay, so the spin, so you can take is the plus half. So the first electron it will occupy, so it will be plus half. So spin is equals to plus half. So what is the correct? So N is equals to 4, L will have up to value 3, and M is equals to 1. Okay, M is equals to 1 for one electron. We are finding the quantum number for one electron from the f orbital. Okay, so this is the, which is the correct answer? A is the correct answer. So like this, they have asked only for one electron in 4f orbital, not all the electrons. Okay, so if the all electrons are there, then M values will be more. Okay, so it will have from this what? L minus L including 0 to plus L. Okay, so it will be what? Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay, so these are the values of M. So they have asked here, the question is only for one electron you are finding the set of quantum numbers. Okay, so we'll go for the next question. Which of the following sets of quantum numbers represent the highest energy of an atom? So we have to find the highest energy. Okay, which of the set? So we'll consider only these two conditions. Which N is equals to, we'll just see this two. So when N is equals to 3, N is equals to 3 means what? It is, the main shell is 3. L is equals to 2. Now see here, L is equals to, I'll write it here, okay? L is equals to 0, 1, 2, 3. 0 is what? 0 means S. 1 means P. This is D and this is F. Now L is equals to 2. 2 means what? It is 3D. Okay. So 3D. So first energy, this is 3D. So this represents 3D. Then second is what? N is equals to 4. So the main subshell is 4. Main shell is 4. Now what is L is equals to 0? 0 means what? It is S. Okay. Then third is what? N is equals to 3. 3, the main shell is 3. L is equals to 0. 0 means what? It is S again. Fourth one, N is equals to 3. Okay. What is L? L is 1. 1 means 2p. So among this, which is the highest energy? Which will be highest energy? So when you are filling the electrons, okay, it will go from lower energy to higher energy. So it is 3D, A. Okay, correct answer is A. So this is the correct answer. Okay, so 1s, 2s, 2p, right? 3s, 3p, 4s, like this, you're going to fill up the electrons. So like that, 3D will be having the highest energy of an atom. So this is the way you're going to solve the question. Next, the quantum numbers plus half and minus half for the electron spin represent. So read out the options and tell me the correct answer. Okay. Tell me the correct answer. So the quantum numbers plus half and minus half for the electron spin represent. Plus half represents what? It represents what? Plus half. It represents clockwise, and minus half represents anti-clockwise. So the correct option is what? It is A. Okay, the correct answer. Okay, so the correct option is A. So next, nodes and rules for filling the electronic configuration. So what are the nodes? We'll see what are nodes and what are the rules of filling the electrons. Now, what is nodes? So nodes is what? It is the probability. Okay, we are finding the region where the probability of finding the electron is 0. Okay, nodes is nothing but the region probability of the finding the electrons. Okay, and the probability of finding the electron there will be 0. So there are two types of nodes. One is radial node and second is angular node. What is radial node? Radial node is nothing but spherical surface region where probability of finding the electron is 0. So it is a spherical surface region. Radial means what? Spherical surface region. Okay. Where the probability of finding the electron is 0. Second is what? So this radial node, it depends upon two conditions. One is what? It depends upon the principal quantum number, and second it depends upon the azimuthal quantum number. So radial node, it depends on principal and azimuthal quantum number. Okay. So here, how is the radial node can be calculated? It is calculated by number of radial node is n minus L minus 1. So this is the formula from which you can calculate the radial mode. Okay. Now, angular node. What is angular node? The planes or planar areas. Okay, the planes or planar areas around the nucleus where probability of finding the electron is 0. Okay, the probability of finding the electron is 0 is nothing but your angular node. Okay, and this angular node, it depends only upon the azimuthal quantum number. So the number of angular mode can be calculated by the value of L. Okay, so total number of nodes. So this is for radial node and this is for angular node calculating part. If you want to calculate total number of nodes present in an electron, okay, around the probability of finding the electron, so that will be n minus 1. So this is the formula from which you can calculate the radius node and angular node. Okay. So what are the rules? So filling up of electronic configuration. So what are the first rule is above principle. What do you mean by above principle? Okay, above principle is what? It is the filling up of electrons from in order of their increasing energy. Now here you can see the diagram here. You can see 1s, 2s, 3s, 4s, right? So these are the different energy of the orbitals. Now here, how the filling up of electron takes place. First, the electron will enter into the s orbital. If the electrons are filled into the next orbital, then the electrons will go to the 2s, followed by 2p, 3s, then 3p, 4s, 3d, 4p, 5s, and etc. So the orbitals are filled in the order of their increasing energy. Okay. Then what is n plus L rule? What is n plus L rule? The energy of an orbital, it depends upon the sum of the values of principal quantum number and azimuthal quantum number. So it depends upon the sum of the values of principal quantum number and L. L is what? Azimuthal quantum number. It depends upon the sum of these two. Okay. Why it is used? Why this rule is used? This rule is used to predict the energy of the orbitals. This rule is used to predict the energy of the orbitals. Lower the value of n plus 1, lower is the energy. If the value of n plus L is less, then the energy is also less. If two orbitals are having, now consider if there are two orbitals and both the orbitals are having same n plus L value, then what you have to see? You have to see the orbital which is having the smaller n value. Okay. So the orbitals having the lower value of n will have the lower energy. So based on this, you can fill up the electrons. So this is above principle. Okay, remember the electronic configuration, how you are going to fill. You have to fill the electrons in various orbital by increasing energy, in the order of increasing energy. Next is Pauli's exclusion principle. Okay, next is Pauli's exclusion principle. And orbital can accommodate at least 2 electrons with spin opposite to each other. Okay. So what is Pauli's exclusion principle? No 2 electrons in an atom can have the exact same quantum numbers. So there are 4 quantum numbers. So no any electrons will have same set of 4 quantum numbers. So you can see this example, how the electrons are arranged. So, right. So you can see here, both the electrons are anti-parallel to each other. So 1s, 2s, right. You can see the second here, first is anti-parallel, the second is in same direction. So this is wrong. The filling up of electrons is wrong. In the third, you can see first is anti-parallel. This both are down. Okay, it is pointing downwards. So both the second and third condition is wrong. So whenever you are filling the electrons, both should be anti-parallel to each other, and no two electrons in a set will have the same four quantum numbers. Okay. Next is what? Hund's rule of maximum multiplicity. So pairing of electron does not occur in an orbitals of the same energy until each of them is singly occupied. So you can see here. Okay, these are the example. Carbon, I have taken carbon is what? 1s2, 2s2, 2p2. So first the electrons are singly occupied. Now this is first orbit is 1s. So first we will add the electrons. So 2 electrons occupied, then it goes to 2s. Then in 2p, first the electrons will be singly occupied. Then they will undergo the they will form the pairing will takes place. So this is the Hund's rule of multiplicity. What is Hund's rule? First, the electrons are singly occupied. Once the electrons are singly occupied, then the next electron goes and pairs with them. Okay. So based on this, we'll solve some questions. So the number of nodal planes in 3px orbital is, okay, we have to calculate the number of nodal planes. Total number of, so here, number of nodal planes. Nodal planes means what? Planar node. Okay, planar node. You have to calculate. So how it is? You have to calculate in 3px. So the number of nodal planes in 3px is orbital is. So on what terms it depends? It depends upon L, right? So for n is equals to 3, what is the main subshell? 3. So L will have what value? L will have 0, 1, 2, right? So here we are going to calculate the for 2px. Okay, we are finding the, so we are finding for 2px, right? So it is what? It is 1. So L is equals to 1. So for 1 electron, we are finding the nodal plane for 2px. So when you have 2px, they are specifically asked for the orbital of 2px. So it will be, L value will be 1. So it is 1. Okay. So next, the number of d electrons remained in Fe plus 2. So Fe, what is the atomic number given of Fe? So Fe is 26. Okay. Then Fe, when it goes plus 2 means what? Loss of 2 electrons. So it will be 24. So write the electronic configuration. When you write the electronic configuration, argon is 18, then 3d 6 and 4s2. Okay, the number of 3d electrons remained in Fe plus 2. After losing the Fe plus 2 means what? 2 electrons are lost. So how many electrons are remaining? It is 3d 6. So how many electrons are there? 3d 6. So the correct answer is 6. Okay. The number of unpaired electrons in Fe plus 3. Now we have to see the number of unpaired electrons. Okay, they have asked the number of unpaired electrons in Fe plus 3. What is Fe? Atomic number is 26. Now write the electronic configuration for Fe. Fe is equals to argon is 18. Okay, argon is 18. Then it is 3d 6 4s2. When it undergoes Fe plus 3, it will be argon. So these 2 electrons and 1 electrons from 3 orbitals, it will be 3d 5. So how many unpaired electrons are there? So when you are writing now, according to Hund's multiplicity, you have to fill the electrons. Okay, how you are going to fill up the electrons? What is the correct answer? Yes. So you're filling the electrons. First, it will be singly occupied. How many electrons are there? 5 electrons. So 1, 2, 3, 4, 5. So how many unpaired electrons? There are 5 unpaired electrons. So correct answer is 5. Consider the ground state of chromium atom. Z is equals to 24. So chromium is 24. Okay, chromium is 24. The number of electrons with azimuthal quantum number L is equals to 1 and 2 are respectively. Okay, so number of electrons with azimuthal quantum number L is equals to 1 and 2. So L is equals to 1 means what? L is equals to 1 means it is, so L is equals to 0, 1, 2, 3. You write it S, P, D, F. So L is equals to 1 means it is P. Right? It is P. So it means it is a P subshell. Okay, P subshell, then L is equal to what? Another condition is 2. N is equals to 2 means it is D. Right? It is D. So first we'll calculate. Now when you are writing chromium, so number of electrons calculated as, so chromium is 24. So write down the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Okay, then the next electron will go into 4s1 and then 3d5. Okay, so total number of electrons we have to calculate. Total number of electrons in L is equals to 1. Okay, so when it is so you know how many electrons you have to calculate in P. You have to calculate the electrons when L is equals to 1. So how many P orbitals are there? Here P orbitals are so 6 plus 6, right? So in L is equals to 1, for that is for P, the number of electrons are how many? 12. And when L is equals to 2, that is for 3 D orbitals, how many electrons are present? D orbitals, yes, 5. So it is 5. So the correct answer is what? 12 and 5. So you have to calculate the number of electrons. So like this, when azimuthal quantum number is given, you have to calculate the number of electrons. So by this, we have solved some of the questions based on the azimuthal quantum numbers, various quantum numbers. Okay. So we'll see. So we'll start with the next chapter tomorrow. Okay. So today's structure of atom questions, whatever I have discussed, please go through. Okay. And thank you. Thank you, students, for answering. Thank you so much. We'll stop it for today. We'll meet you tomorrow.